Hey, I'm David Moon. I just finished my PhD at the University of Michigan, and today I'm going to tell you about our paper, Syntactic Completions with Material Obligations, which is the focal chapter of my dissertation. The goal of my PhD work has been to support live programming experiences. And when I say live, I mean semantics on tap. Your program semantics should be freely available and queryable whenever you want them throughout development. Of course, this isn't the full picture. All of these semantics are downstream of your program's well-formed syntax. This means the flow of semantics can be compromised by syntax errors. A naively implemented parser might simply fail on the first unexpected token and produce no structure, in which case we no longer have a live program. Instead, we just have some dead text. To keep the semantics flowing, modern parsers will try to recover from unexpected tokens so that they can structure as much of the program as possible. Often this involves some form of implicit repair around the error site. Panic mode is a common and especially simple form that limits itself to deletion-based repairs. On encountering an unexpected token, a panicking parser will drop tokens around the error site until parsing can resume normally around the dropped tokens. Panic mode is easy to implement, but it can lead to large skipped regions of code with no semantic feedback. More sophisticated methods consider the full space of textual repairs. Here, a drop-down menu enumerates and sorts different possible repairs to the first line of the program, where repairs now combine insertions in green with the deletions in red. The benefit of incorporating insertions is that this minimizes skipped regions of code, as shown in the first 3 repairs. On the other hand, there are often many similarly structured insertion-based repairs, as shown in the last 4. It's often unclear a priori how the parser should rank such choices, while asking the programmer to disambiguate can be distracting and risk information overload. In this paper, we consider repairing errors not just with text, but with a more abstract set of what we call syntactic obligations, which I'll now demo in our prototype editor, tylr. All right, so here's tylr. It's just almost like a text editor, but you can see that there's some funny shapes on all the tokens. The first and most common kind of obligation is the operand obligation. Just like holes in structure editors, they act as placeholders for missing terms. We can understand missing terms more generally as an inconsistency in multiplicity. In each of these positions, we expect one term but find 0. Dually, it's possible to expect one term but find many. If I delete this comma here, tylr inserts an infix obligation to join together P1 and P2 into one term as expected by the surrounding parentheses. And notice how this abstracts over the various possible operators that strictly textual repair-based approaches would consider individually. With such natural defaults at hand, it starts to become reasonable for the parser to choose a repair and materialize it to the programmer such that they and the system are on the same page. Sadly, this is often not the case with IDEs today. There are still many situations where there isn't a natural default, which typically arise when have to do with the placement of delimiter obligations. It's perhaps natural here that when I delete the delimiters to leave obligations behind in their place, but the choice is less obvious when inserting forms in the middle of your program. So here I'll start to retype this line over here. And here, Tylr has chosen to insert the matching in at the end of the line, which is what we want in this case. But it could have been that I meant to bind the following expression to my new variable. In that case, I can simply insert the in delimiter where I want it, and Tylr will remove the now redundant obligation. There's one more kind of obligation in Tylr's toolbox. Here, Tylr has inserted a prefix obligation to buffer between the expected pattern sort and the provided type sort. These appear rarely in this particular language, but you could imagine postfix obligations appearing often in a language like Haskell when constructing the pattern that begins a top-level definition. Okay. So that's it for the demo. Powering tall Tylr is a novel parsing framework dubbed tile-based parsing because raw tokens are first molded into tiles before they are parsed into terms. A tile-based parser consists of a melder and a molder. The melder is an error-handling generalization of operator-precedence parsing, or OP parsing. And there are many things to love about OP parsing. It's simple to implement and runs in linear time. The method generalizes naturally to handle errors. And especially nice is that it enjoys the bounded context property, meaning it's possible to parse any subrange of input knowing only the single tokens on either side of that range. And what this gives you is parallelization and incrementality for free. And so I think this makes OP parsing an especially appealing foundation for modeling program editors. Meanwhile, the molder assigns molds to tokens so that they can be melded. Later, I'll talk about how this eases the grammar restrictions of traditional OP parsing and why I think molds are a better primitive to design for than the items that underlie methods like LL and LR parsers. First, let's talk about melding, in particular how melding extends OP parsing with obligation-based repair. Here I'm referring to the method as first described by Floyd in the 60s, which goes beyond just infix operators, as OP parsing is commonly understood to be limited to today. This method described by Floyd is an early pioneer of shift-reduced parsing. So we're going to go left to right, stopping at each of these points, and construct our term bottom up. And the spiky tokens at the ends are marking the start of input and end of input. At parser generation time, we can derive a set of precedence comparisons between symbols, which we'll use to drive the decision to shift versus reduce at each point. So at the first stopping point, we have a less than comparison. And what this means is that let begins a right descendant of the start of input symbol. And if we see a less than, then we're going to go ahead and shift. We see another less than, so we're going to continue shifting. And then now this time, we see a greater than symbol. And what this means is that we've reached the end of a term. The colon is the delimiter that closes the X. Term. And so we're going to reach back, find the nearest less than symbol, and we're going to reduce that and continue comparing the tokens on either side. And we continue like so. In this case, we encounter an equals relation, and this means that these are matching delimiters. And like less than, we'll use this to shift. We'll interpret this as a shift decision. And we can continue that similarly. And then finally, we reach the end, and we are happy. OK, so now let's consider how we can handle errors when doing this. So I'm going to consider parsing this parsing this input, but I'm going to take out these two tokens here. And let's see what happens when we reach that gap. So traditional OP parsing, it would find that there's no precedence comparison connecting the let and the num type. And so it would get stuck and it would fail, and that would be that. But if we recall from the previous parse, we saw that were there an x and a colon, then we would be able to just continue parsing. And so one of the generalizations we make to OP parsing is to generalize single-step precedence comparisons to multi-step precedence walks. And so in this case, the tokens that we generate in between the compared tokens are the completed insertions that we use to repair the code. Now, so far, this is not that different from just purely textual repair. But we can, with our language of more abstract obligations, we can instead choose to pick these natural defaults instead. So here I might replace the x with an operand obligation and the colon with an infix obligation. Or I might go further and just combine them into a prefix obligation here. And if we take a look at these various options, Tylr would choose the top option over here because it inserts the fewest obligations. But whatever choice is made, we show in our paper that for any grammar where we extend that grammar of tiles with additional grout forms that can be used to that can be used to serve as these default completions, we can show that melding is sound. The output is always grammatical, which is actually not the case for traditional OP parsing, and it's also total. Output is guaranteed. Okay, so that's melding, and now we'll touch on molding. And given that melding is sound and total, one nice thing about the meldr is that we can make choices between different possible molds simply by the same trick of minimizing obligations. So I'll show you an example here. So here we have this is the grammar that we use to that we represent in this language, and you'll notice that there are multiple parentheses that appear in this grammar. And if this were a purely textual grammar, this would actually fail to be an OP operator-precedence grammar because the appearance of the open parentheses across different positions causes there to be ambiguities in the precedence comparisons that you can make between that opening parentheses and other tokens. So what we're going to do here is we actually assume that these are just unique and distinct tokens, and we are going to simply try each of these options. And because we have this sound and total guarantee, we can simply inspect the results and see which produces the least obligations. And in this case, when we are considering which of these open parentheses choices to take, we see that the pattern parentheses produces the minimal obligations. So that's tile-based parsing. It looks like I'm out of time, but check out our paper for also our user study in which we considered how participants respond to obligations appearing in the editor. And yeah, there are some interesting takeaways about directly rejecting obligation-based repairs that I hope you check out. And that is all. Thank you.
Thank you.